Hi, so today I'm going to talk about the RISC-V-based AI MCUs. I'm Professor Dr. Mehdi. So this is my biography. I was the ex-professor Hunan University of Art and Science, senior consultant for the total artificial heart, and I'm a senior consultant for RFIC, MMIC, MCU, and nanotechnology for the radio astronomy. I'm the CTO and co-founder for the Upswing Robotics for Biomedical Devices and CTO co-founder for the Space Radio Astronomy for radio astronomy devices. I'm also co-founder for the Upstream Heart Transplant for the Total Artificial Heart Transplants and LVADs. I'm a patron for Journal of Medical Electronics and Mechanical Circuit Support and patron for International Society of Medical Electronics and Mechanical Circuit Support. So this is the content. I'm going to talk about the core team into the introduction, RISC-V CPU diversity, Upstream Robotic RISC-V based AI MCU, space radio astronomy RISC-V-based AIMC, and automotive industry RISC-V-based AIMCU. Eventually, in the end, I will talk about the RISC-V-based AI MCUs and in the end, the conclusion. Here we go. So we have the core team. I'm the Professor Dr. Mehdi. I'm the CTO and the head of the MCU and mechanical structure for the total artificial heart. So, secondly, I'm also the CTO for the space radio astronomy for the receivers transceiver design for the space applications and MCU. We're going to start with the introduction. Here we go. So what are the trends in hardware design right now? So right now we can see we have Intel, AMD, NVIDIA, which captures the 95% market, and they are no free IP. So eventually you can't use these things, and also the most important thing is the performance characterization required a lot of effort, hard to get right. It's not easy to get it. So we have some very good options. It's like we have something like RISC-V, which is kind of like a free IP, and it can do a good performance to characterize the and don't require a lot of effort for the characterization, and we can easily get it right because it's a free IP. We can change the contents. So right now we are in a golden age of silicon diversity. You can see from the picture, a woman and a robot. It's like a AI personalization. She's like guiding him how to what to do today, and she will tell her. The robot is like kind of like a secretary for her. So we have a silicon heterogeneity, architecture varieties. We have multi-vendor. We have so many vendors for silicon landscape. So different landscape we have like silicon carbide, 3.5, silicon gallium, and we have so many vendors for this thing. We have so many design composability. So we have so many designs, we can choose anyone, which is better. And on the right side, you can see the pictures, an aeroplane, there's a car, and the boat is moving, and this is more like ubiquitous AI compute for all of this connected with each other. This is, we can say, the golden age of the silicon diversity. Okay, the RISC-V, normally it was origin story. Pronounced as like a RISC-V. It was started as a research project in 2010 at UC Berkeley. Its commercially ISA were too complex and presented IP legal issues. The like ARM and different kind of like SIVA, they have like commercialized too complex. So the RISC-V defined an ISA specification. So the two main specifications were the user level and privilege level. So the user level is currently frozen at version 2, which was released in May 2014. And the privilege level architecture is currently at version 1.10. RISC-V is available freely under a permissive license. So you should know one thing, that RISC-V is not a company. It is a CPU implementation. So, so if we have an open source hardware like RISC-V using processors, we can easily scale up because it's free IP. We can do extensible, we can do efficient, we can do may increase its efficiency. to and also it can be stable because we know everything about this free IP. Okay, so now we'll talk about the RISC-V CPU diversity. There are different type of CPU, but we will talk about the one company, which is like the pioneer, a co-founder for the RISC-V processors, and here we go. RISC-V market currently like research by SHD Group. They said the system on chip revenue it was 2.8x in 2023, which will lead to 15 times more from 2023 to 2030, which is too much. And if you see from here, we can see the mobile market where we can see we have the Wi-Fi, we have the Bluetooth, and we have many like the smartphones and everything, the media tag and this kind of things, which will increase the market. And we have 5G networks, we have like MPU, MCU for Renesas, and also the storage devices which we can use for the RISC-V processors or RISC-V technology for these all of these things. On the right hand side we can see we can large scale the AI and ML machine learning and artificial intelligence. We can scale it large because it's very IP. We can do the transform. We can also use these kind of things in cabin radar, CMOS sensors, auto DVR cam, auto MCU, and display and touch. And many places we can use this S5 market, which is growing rapidly, very fast. So like we will only focus on one company, which is NDS Core CPUs. So they are lined up like they have different categories, and our company mostly depend on this company. So like they have categorized like AX63, which is power efficient, AX65, which is balanced, and AX66 and AX is extended, and AX60 SE is a future. So if we see from the 40 series, the category 40 series H stage superscale, it has the power efficient of which is named by N45 and NX45. And if we want to increase it, we can go for the AX45 MPU. And we have a 27 series, which is 5 stage. We have 25 series, which is 5 stage. And afterwards, we can see which one we want. We want a power efficient, balanced, extended fusor. So we can then choose which one is much better for our project. And it is being categorized by the embedded control, computational, Linux, and fusor. Here we go. Now we talk about our company, Upselling Robotics, which is basically for the biomedical devices, which is mostly depend on the RISC-V processor-based MCUs. So here we go. So our like Upstream Robotics currently is making total artificial heart, which will be implanted inside humans. So the main objective for this thing currently in the artificial heart market, the processors are mostly outside the body, and so they don't use mostly they use Texas Instrument or other Android, Arduino kind of processors for the total artificial heart. But we because we want the chip should be inside the body, so we have to make a custom design. So we choose like a specific RISC-V based IP because it was free. Also, we need quite artificial AI deep learning inside. So we use NDR's Endel 1350 based RISC-V process CPUs for this project. So on the right side, you can see a big emulation board, which is used to test the CPU after fabrication. So, and then we can use this thing in the artificial heart. Okay, so this is the block diagram on the left hand side, the CPU of this thing, which we will have. We have a CPU of a RISC-V, which will have a 32 KB L cache and 512 KB cache DMA inside. And then we will have a custom design IPs for the ECG and everything, heart rate monitor, battery sensors, and everything inside. And we have our own IPs and use third-party IPs for this project. So we use the NDR's NDL for the total artificial heart. Okay, the next company which I'm talking about, the Space Radio Astronomy RISC-V-based AI MCUs. This company is mostly based on the astronomy projects like transceivers for the space application. After we getting the signals, we want to do some calculation. So we use AI MCUs for the RISC-V based. So here we go. So this is like space radio astronomy. Like on left hand side, you can see the transceiver getting a terahertz signals from the skies, and then after getting the signal, it being amplified and then goes some stages and it reaches the signal level, which is where and then on that level, like we can say. On the power meter side, we can quick connect with the MCUs, AI-based, RISC-V-based MCUs for terahertz receiver. After getting the signals, we can do the some digital signal processing, DSP, and other simulations to get to understand the signals. So we use normally RISC-V-based processors, NDS technology, which is the 1350 because it also have a AI, artificial and deep learning uh, project inside this CPU. Okay, this is the block diagram, the same as the company Offspring Robotics for the MCU. We can see that it has the same CPU, RISC-V based, and it has a 32 KB L cache, 512 KB yeah, the cache, and our DMA the same, and the custom IPs for the space radio astronomy project. Okay, now we're going to talk about the automotive industry, which is RISC-V based AI MCUs. Okay, the automotive is kind of like a sandbox. In decades, automotive has been seen as a separate ecosystem, long developed cycle. It has a unique requirement, complex tire systems, extremely resistant to change, closet analog as industrial. So automotive semiconductors is more like its temperature should be minus 40 to 125. It can be at this temperature, and the product life cycle should be 10 to 15 years. The industrial semiconductor focus mostly on rigid reliability, diverse application, shortest development cycles. So the SVD revolution, which is we call software-defined vehicle revolution, we can see the explosive market growth. Expect OED software and digital investment to triple by 2035. And also in industrial transformation, we can see 75% of industry leaders expect software-defined experience to be core to automotive brand value by 2035. And mostly the shift from the traditional hardware-dependent model to flexible software platform, which is we call software-defined vehicle, and also the growing emphasis on predictive maintenance and AI-powered diagnosis. On the down, we can see ARM, which is very difficult to scale, which is not free IP, PowerPC, and many tri-core. On the right side, we can see Arrow software-defined vehicle. We use RISC-V, which is clean, simplified, centralized, software-first approach. Okay, and this is more like the best approach for the software-defined vehicle if we use RISC-V. On the right side, you can see the graph sales, software-defined vehicle based or centralized domain architecture by type of OEM. You can see the sales for the incumbent. It reached from the 2019 to 2026 from zero point 0.2 million to around 3.8 million. And for the same disruptor, we can see the sales from 2024. It was like around zero point 0.1 million. It can reach to 2 million by 2036. So it means the software-defined vehicle revolution in practical terms. It is like more like modern constellation architecture, such as centralized domain and zone architecture offer several key benefits. Integration of high performance computing within constellation ECU. It can decoupling of hardware and software for greater flexibility and scalable use of advanced technologies such as Ethernet for fast communication between ECU and vehicle sensor. Seamless connection of vehicle system and sensor to the cloud, enabling frequency and reliable over-the-air OTA updates. Sophisticated interconnect vehicle feature that use cross-domain and cloud data. Reduction in the number of physical components such as cable hardness, which decrease vehicle weight, are critical factor for improving the range of electrical vehicle. Simplification of physical architecture result in easy manufacture processing enhanced and potential lower overall cost. So RISC-V is strongest in the most significant area of both intelligent automotive and industry. Safe, secure, scalable development time, independent, and right sizing intelligent. Here we go. So now we can see the opportunities in regional development cycle. China predicted to be the locus of SDV RISC-V industrial automotive, forecasting top 10 leading OEM by software-defined vehicle sale market share in 2030. You can see the BYD, which is the highest 131%, and then we have BMW, Tesla is 24.7%, the Chinese manufacturer 7%, and the Mercedes-Benz is like 5%. On the middle, we can see intelligent industrial automation unit by region from 2022 2023 30. You can see it scales from 6.7.8 to about 11.9, which is quite high, also including the Americans, the EME, the European, and the Asian ones. And the RISC-V processor on the right side, left, the figure, the the chart shows the RISC-V processors in industrial application by region 2020 to 2030. You can see it scales from about 5.5 to it can reach 2030 to 25, which is quite high. The industrial application region for the RISC-V. So we should go for the RISC-V in future. Okay, so we can now going to talk about the one which we use in the automotive, which you use in the biomedical device space application. Which MCU normally they have the best ones right now? So we talk about the RISC-V based AI MCU NDS NDL 1350. It is a high performance, efficient deep learning accelerator for end-to-end point interface. It has configurable MAC from 32 to 4096 INT8. Maximum performance is 8 tops at 1 GHz. Configurable local memory can go to 16 KB to 4 MB. Multi-dimension DMA, 464-bit AXI bus interface, NN type CNN interface, NN model. Image and video are like LXNet, VGG 16 by 19, MobileNet V1, V2, V3. ResNet is 8 by 50, Tiny YOLO V1, V2. YOLO V1, V2, V3, V4, and SSD MobileNet can go to V1, V2. Inception V2. It has a speech, voice, and audio LCSTM, can support RNN support, GRU support. Operator like it can support convolution to the depth voice convolution, point voice convolution, transpose convolution, dilated convolution, element wise like add sum, and fully connected activation. And it can go up to pool, max, upsample, concentrate, batch, normalization, channel padding, and also operator fusion NHWC data format. So the application, like we talk about the RISC-V based and AI MCUs can go to like on left side IoT device like TinyML on edge and biomedical device, space radio, astronomy, automation industry, smart sensor, sensor hub, wearable, smart home appliance, robotics. So NDL TM3050, you can see the block diagram. It has DMA, general matrix, multiple local memory, convolution accumulator, custom element-wise data processing pooling feature. Now we go for the conclusion. So RISC-V conclusion for all computing devices. RISC-V is emerging as a major application platform. RISC-V help in lowering SoC design entry barrier, extremely low power consumption, high computing efficiency, AI personalization, AI computing facility. It is the golden age of silicon diversity and high performance for the CPU roadmap. So these are the RISC-V companies' dependency You can see so many companies which is dependent on the RISC-V, like Samsung, Huawei, and many other big companies. They are dependent on this RISC-V based. So this is my company, Option Robotics and Space Radio Astronomy. We have partners Skyworks, Chip Motion, the Chinese company, eFabless, IC Cafe, and USTC. So they are our partners. So Option Robotics, Space, and thank you very much. If you have any questions, you can ask me anytime.